Astronomy Club of RSET. May I invite Professor P.S. Rijit, Principal, Rajagiri School of Engineering and Technology, for the inauguration of the Astronomy Club. Over to you, sir.
Good afternoon to all. Respected Professor A.N. Ramaprakash, who is delivering the talk today, and the coordinators of the Astronomy Club, Dr. Rinku Jacob and Dr. Karthik D. Dear participants, I am extremely happy to inaugurate the Astronomy Club of Rajagiri School of Engineering and Technology. Astronomy generally study planets, stars and other celestial bodies, and they use ground-based equipment such as optical telescopes and space-based equipment such as the Hubble Space Telescope. Some astronomers study distant galaxies and phenomena such as black holes and neutron stars. Observing the moon is one of the easiest ways to get started with astronomy. You can track the lunar cycle and use binoculars or a telescope to see how your view changes. When the moon is full, for example, it tends to be dazzlingly bright and one-dimensional. Statistics say that for every professional astronomer, there are 20 amateurs. And the last few years, the majority is really showing how influential they can be in the scientific community. In recent years, amateur astronomers have stunned the world by beating the professionals to a number of first discoveries. In 2012, amateur astronomers were the first to detect two strange objects impacting with Jupiter's atmosphere. More recently, they have spotted dozens of new exoplanets, including many that could possibly be habitable. During the International Year of Astronomer, that is in 2009, amateur astronomers played a major role in the organization of astronomy outreach activities that really brought the global event to life. Now, universe awareness is inviting amateur astronomers to make a difference by inspiring young children with the wonders of the cosmos and helping to build a solid future for astronomy and cosmic discovery. Between 4 and 10 years is the perfect age for children to get in touch with science for the first time, and astronomy is by far the most inspiring and easy to access of all the scientific topics. Research shows that encouraging children to have fun and play while learning and by letting them observe independently and research for their own answers rather than explaining everything to them encourages scientific thinking. You don't have to be a teacher or an expert on pedagogy, but must be enthusiastic and let the universe do the hard work for you. With these introductory words, I announce the inauguration of the Astronomy Club of Rajagiri School of Engineering and Technology. And today we have got an eminent personality for the first lecture of the Astronomy Club, that is Professor A.N. Ramaprakash, who is Scientist G and Head Instrumentation of Inter-University Center for Astronomy and Astrophysics. And his topic is also very relevant. How do I transform from amateur to professional astronomers? And I hope his talk will be giving more light on these astronomical facts. And I welcome you, sir, for delivering your talk. And I thank everybody, every participants present here. And once again, I thank everybody. Thank you very much.
Thank you, sir, for your extended support in the formation of Astronomy Club and its inauguration. So let me introduce the speaker again, a brief introduction about the speaker. That is Professor A.N. Ramaprakash, who is the head of the instrumentation at IUCAA, Pune. He is an engineer by profession, and he is also a scientist. He works in the interface between astronomy and engineering. Professor Ramaprakash is an internationally known astronomy instrumentation engineer, and his lab at IUCAA is providing instruments to many telescopes all over the world. Professor A.N. Ramaprakash did his BTech in electronics and then went on to do his master's and PhD in physics. He has been a visiting fellow specializing in the area of astronomy at the California Institute of Technology, USA, and has also been a postdoc fellow in the discipline of instrumentation at the Institute of Astronomy, Cambridge, UK. He joined IUCAA in 2000. Professor Ramprakash also holds academic positions at the Indian Institute of Astrophysics, Bangalore, Center of Excellence in Space Sciences, hosted by Indian Institute of Science, Education and Research, Kolkata, and California Institute of Technology, USA. He has contributed in various capacities to many projects at the national and international levels. I will list a few of them. He is the principal investigator of the project Devasthal Optical Telescope Integral Field Spectrograph and is the instrument principal investigator of the Solar Ultraviolet Imaging Telescope onboard Aditya L1 mission, which is the first dedicated solar mission of the ISRO. He is the associate program director of the India 30-meter telescope project funded by the Department of Science and Technology and Department of Atomic Energy. He was a co-principal investigator of the collaborative project RoboPol, which is a specialized photopolarimeter designed specifically for 1.3 meter telescope at the Spinakes Observatory commissioned in 2013. He was the co-principal investigator of the collaborative project Wide Area Linear Optical Polarimeter, as well as the RoboAO, which is the first autonomous laser adaptive optics for few meter class telescopes. It goes without saying that Professor A.N. Ramaprakash has published extensively with over 100 publications to his credit. He is also a thesis advisor and a postdoctoral advisor. He is the apt person for talking about the interface between astronomy and engineering. I hope this webinar will be very beneficial to young engineers and also the student community. Now, may I invite Professor A.N. Ramaprakash to deliver the talk. Sir, over to you, sir.
Thank you, Dr. Rinku Jacob, and thank you, Dr. Srijit, for being here with us today, and also Dr. Karthik, which I understand has been part of the organizing team for this astronomy club. I'm really privileged to be speaking to this big audience of engineers. And I looked at the list of participants who have registered for this webinar, and it covers all streams of engineering, right from mechanical, electronics, instrumentation, and whatnot. So I would try to address my presentation to that kind of an audience to make sure that each of you, whichever branch you work in, gain some understanding of what astronomy is all about and how you may be able to contribute to the rapid progress astronomy and astrophysics is making these days. So to start with, my title says from amateur to professional. It doesn't really mean that you need to be an amateur astronomer to become a professional astronomer. That's not the only path available. So let me clarify at the beginning itself that the question, is it necessary to start as an amateur to become a professional astronomer? Absolutely not. That's not necessary. But since we are today in this forum of the inauguration of the Astronomy Club at RSET, I thought the title would be appropriate, but I will not specifically tuning my talk towards amateur astronomy activity. I would try to keep it as general as possible. Now, the second question, which might come to your mind in this context, is it necessary to study a particular subject? You know, many people may say that unless you know a lot of physics, a lot of mathematics, etc., you cannot contribute to astronomy in any way. That is also not true. Absolutely not. It's not necessary that you should have a very deep understanding of physics or a deep understanding of mathematics to contribute meaningfully to astronomy in today's world. But of course, if you want to get into the astrophysics part of things, the physics part of things, so you need a physics background and maths background. But that is not to say that to work or contribute to astronomy, you don't need you need a physics or maths background. But what is necessary is the following. It's a very demanding and challenging field. We're trying to break new barriers, new boundaries of human thinking and technology, science and technology. Almost everything we try to do in astronomy. And therefore, you need to be very good at what you're doing. Whichever subject you specialize in, you need to be very, very good. And that's only a requirement. It's not required that you need to be a physicist or a mathematician or a chemist or a biologist to be in astronomy. You can be in any field, but still contribute. So let me try to bring that aspect of astronomy out in the context of a few projects which we are involved in India. And therefore, that gives you a glimpse of what all areas and which all ways you could contribute to astronomy. To understand this, let me pick firstly a project which is called the 30-meter telescope project, which is one of the most exciting instrumentation work which is happening in these days. And it is being a collaboration of IUCAA, where I work, Indian Institute of Astrophysics in Bangalore, and ARIES is a sister institute in Nainital. These three are the PI institutions which form India TMT. And we are collaborating with, of course, a large number of universities and other institutions and industries in the country. So let me give a glimpse of this project, what it means and where it is, and how you could contribute to this program as an example. Let me take a step back. At the moment, the world over, there are several international efforts being carried out to build a set of large telescopes, and the three of them is listed here. These are all ground-based facilities. One is the 25.5 meter giant Magellan telescope, and the 30-meter diameter 30-meter telescope, and the 39-meter diameter European extremely large telescope. These telescopes are being designed, planned, and built by various international consortia. And these consortia around 2006, 2007 approached India to see if there is an interest in India to participate in any one of them. And then we went through a very detailed evaluation process, whether we need to participate in any of them, and also to select which one of these is most suitable for us and what level we should participate, how many people we would need to have in order to make best use of these facilities, and so on and so forth. And at the end of that process, as a community process, we decided finally to join this 30-meter telescope project at a 10% level participation for various reasons. Anyway, so where is the 30-meter telescope going to come up in? It's in the middle of the Pacific Ocean, the series of islands called Hawaii. So most probably the TMT will be located in one of the Hawaiian islands, what is called the Big Island, and somewhere out there. And the participants of the observatory are coming from India, from China, from Japan, from Canada, and from a set of institutions in California, and potentially the wider astronomy community in the US. Two institutions in these countries are joined together to form a corporation which will build this facility, most probably on this mountain called Mauna Kea. So in India, as I mentioned earlier, the effort is spearheaded by the three institutes, IUCAA, IAA, and ARIES. Now, the reason why we chose this facility, this location, is that it is eminently useful. I mean, in the northern hemisphere of Earth, it's one of the best known site for astronomy, carrying out astronomical observations, because we don't want a site which are unusable in many nights because of cloud cover, dust, or something. So the number of nights which are usable has to be very high. There should be very little water vapor in the atmosphere because many of the radiations coming from extraterrestrial objects get absorbed by water vapor. So the atmosphere should be very dry and very high so that there is very little atmosphere above the observatory, and the location should be as cool as possible, etc., etc. There are many criteria which we apply to identify a suitable observatory location, and Mauna Kea happens to be one of the best. I will skip that box for today. So this is a view, a photograph of the top of the mountain as it stands today. So there are many observatories already existing at the summit of that mountain. This is the top of Mauna Kea, at about more than 4,200 meters above sea level. Existing big observatories, many of them are located on top of this mountain. And here is an artistic impression. This is not a real picture. It's an artistic impression of where TMT will be located on top of that mountain. It's not exactly at the top of the summit, but slightly off the summit towards one side. Now, in order to understand the scale, I mentioned that this mountain is 4,200 meters above sea level. So you can see the clouds there. The clouds are mostly below the summit of the mountain. You can see the clear blue skies which are visible from that location. And this observatory itself is an enormous facility. This height is about 18 stories, like equivalent to an 18-story building. So if you compare that with, for example, like a large structure which we all know about, like the India Gate or the Qutub Minar, you want to build a structure as large as that, as high as that, more than 18-story high. On top of this mountain, this is a volcanic mountain, extinct volcanic mountain, which is 4,200 meters above sea level, and that's half the height of Mount Everest. So it has to be an engineering marvel to go up there and build these facilities. Let us try to understand what it involves to build such a facility. As I indicated in the beginning, the primary mirror of the telescope is 30 meters in diameter. But that mirror is not made of a single piece of glass. Nobody can make a single piece of glass which is 30 meters in diameter and has the right shape to collect light from celestial objects. So the primary mirror is made of about 492 individual hexagonal segments joined together to form a single surface, as illustrated here. So this is the primary mirror of the telescope. You can see these hexagonal segments. Each of them is about 1.4 meters across. So you put all of them together, edge to edge, and align them together to become one primary mirror of 30 meters in diameter. So in this telescope, there are three mirrors. M1 is the primary mirror, which is shown here, which is a segmented mirror made of 492 segments. So light from celestial objects come in this direction from top to bottom, fall on those primary mirror. And this is a concave in shape. The beam converges and hits this secondary mirror. And then the secondary mirror reflects it back to this tertiary mirror. And then the tertiary mirror reflects it sideways to one of the instruments on these two side platforms here. And these instruments are the ones which analyze the light in various ways to provide us the information about the celestial objects which we are studying with the telescope. So this is a three-mirror telescope system. To put this in perspective, this is a very old photo of a 3.6 meter diameter telescope, which was under construction at that time when this photo was taken, but now it's finished construction, as had already been installed and commissioned in Nainital by ARIES, which is also one of our partner institutes in TMT. So ARIES has commissioned this telescope in Nainital, and this is the largest observatory in India at the moment. So if you fit this observatory, to scale it down, it will kind of be at the same size as the third mirror of the 30-meter telescope. So the primary mirror is 30 meters, secondary mirror is 6 meters or larger, and then the third mirror, which is in the middle, that itself is the size of the largest existing observatory telescope in India. So that's the scale at which we are trying to jump from being part of this project. I'll skip this text here. Maybe I'll answer that later if there are questions. But as I mentioned before, this India TMT consortium is led by 3 institutions: ARIES, which operates the 3.6 meter diameter telescope, which I just showed, Indian Institute of Astrophysics in Bangalore, and Inter-University Center for Astronomy and Astrophysics in Pune. This whole activity of India TMT is coordinated by India TMT Coordination Center, located at the premises of Indian Institute of Astrophysics in Bangalore. And its activities are overseen by a project management board. And then Professor Isha Reddy is the program director for the project, and I am the associate program director. And this project is funded jointly by the Department of Science and Technology and the Department of Atomic Energy in India under this Mega Facilities for Basic Science scheme. And our oversight from the DST and DAE comes through an executive council. It is co-chaired by the Secretary of Department of Science and Technology and the chair of the Atomic Energy Commission in India. And of course, many other institutes and centers and universities in India are actively participating in this program. So you name any institute, I think they will have an interest and a contribution to make. So what are the contributions before that? So this is just a brief history of the program. We started, as I said earlier, around 2006, 2007, and this overall project proposal and approval process took a long time. And finally, on 24th September 2014, the Union Cabinet, chaired by the Prime Minister, announced the approval for India TMT program. And then subsequently in December, we formally joined the project, where the Minister of Science and Technology signed our joining of the project. From 2015 to 2025, we had been executing various work over the last decade or so to enable building of this facility. And moving forward, the actual construction of the International Observatory on Mauna Kea in Hawaii is expected to start in 2025. And the construction itself will take 10 years to complete. So you can imagine it's a 10-year-long construction progress to set up the observatory on the site. And then from 2033 onwards, for another 50 or more years, it will be used for various astronomy and astrophysics scientific activities. So that's the kind of, the overall time scale of these kind of projects. They started 2007. By the time you start observing with the facility, it will be more than a decade from even now, 2033 or 2035. So this is a really complex. You can imagine that these are really complex facilities. And the world's best countries, advanced technology countries like the US, Canada, Japan, India, and China are all struggling to build the components, the engineering marvels that will form part of this facility. So what is India's role in building this observatory? About 30% of our contribution is given in cash for meeting various common expenditures at the observatory location, like the building of the road, the electricity, and so on and so forth. That's a common pool. But the remaining 70% of our contribution will be made in kind. It means components of the observatory will be built in India and sent to Mauna Kea and assembled there to form the final observatory. So this includes all kinds of activities, many hardware subsystems and software subsystems for the observatory, actual people working for the observatory, and various kinds of services provided by us. So the entire gamut is covered in the contributions. This is just a collage showing what each of the partners are roughly contributing. For example, the USA is building certain number of these mirror segments and polishing them. Then the civil work on the mountain is mainly managed by the United States. Japan is making this very complicated telescope structure, which holds together all the three mirrors in a very stable way, and so on and so forth. And I will come to what our contribution is. And most of our contribution in the hardware side focuses mainly on the primary mirror of the telescope, the heart of the telescope itself. So let me try to explain what that is. So this is just a close-up view of the primary mirror of the telescope. As I said earlier, it's made of 492 individual hexagonal shaped segments. Each of these segments have to be handmade one at a time. And if you take just one segment out from here, you need 500, sorry, before this step back, 492 plus 82 different extra segments. So we have to make about 574 segments. Why this extra? That is because this entire mirror surface can be divided into 6 sectors. And at each radius location from the center, the mirrors are identical. So as you move away from, radially away from the center of the mirror, the shape of the segments change. So if you count like that, there are 82 different shapes which are required to form one sector, and there are 6 such sectors. So you need 492 segments to fill the mirror, and then 82 spares, so that you, in case something happens or for various operational reasons, you get one of each type extra. And these mirrors are extremely difficult to manufacture. Very, very difficult to manufacture because they all should form the surface of a single mirror. The polishing should be so good that the surface micro roughness should be less than 2 nanometers RMS. 2 nanometers. Each surface has to be polished down to a level of such that the roughness is less than 2 nanometers. And these 492 segments have to be aligned together with respect to each other to 20 nanometer accuracy. You can imagine there are almost 500 segments. They form an area of a small football field, 30 meters in diameter. And that entire surface has to be kept exactly the right shape with 20 nanometer accuracy. That's a challenge. And this mirror is not going to sit there like this on a surface and just static. This mirror has to move around, like all telescopes which you have seen. The mirror has to turn around and point at different locations in the sky to observe different parts of the sky. So this entire thing is a moving mechanism. It's not a static mechanism. It's a dynamic moving mechanism. So while the whole thing is moving around as a pointing at different parts of the sky, it should retain its shape as a single mirror to 20 nanometer accuracy. So those of you who are engineers out there, especially mechanical engineers, can immediately see what a challenging problem that is to address. And you also see, if you are a control system engineer, you would see if you have 492 of these parts, all trying to move relative to each other, you need to sense motion between them at a small fraction of 20 nanometer, immediately sense such a motion, and then immediately compensate for that so that the mirror maintains its shape overall to 20 nanometer accuracy. That's a control system problem. It's an electronics control system, a sensor, transducer, actuator control system problem for electronics or control system engineers. For mechanical engineers, how to make sure that these mirrors stay aligned together so that each of these mirrors do not experience any of the effects due to gravity, temperature changes, wind buffeting and wind blowing across them is a massive challenge. Okay. So having said that, I also have indicated that the main contribution from India to this project is related to this primary mirror and its subcomponents. So if you take one of these segments, any one of these segments, I've indicated that one segment, one hexagonal segment in this gray thing. Now we are looking at that segment from the bottom, from under the segment. So you can see this very complicated optomechanical assembly here. And this assembly has all these units which are attached to the edges of each of those segments. So these are sensors, we call edge sensors, two at each of the hexagonal edges. And if you think of another edge of another segment coming next to this, the sensor part which is on that segment and this one will form a capacitor, or a sets of capacitors. And those capacitors will tell you if there is any kind of relative movement between this segment and the segment which is butted against this edge. And so on this edge, so on this edge, etc. So these two sensors form a part of a capacitor along with the similar parts which is coming from the other segment butting against this edge. And they will form a capacity sensors, and they will tell you how the that particular segment is trying to move relative to the other segments, and therefore give an information about what corrections to be applied. Similarly, these three units are actuators. These actuators then get feedback from these sensors and then correct the location and the position and the clocking of these segments in real time. And this entire complex optomechanical assembly called the segment support assembly allows you to mount these segments and hold these segments in a way that is gravity invariant, irrespective of in what direction this segment is pointing. It shouldn't feel the bending effects of the gravity, and therefore it should not change its shape. Remember, we need to maintain its shape with 20 nanometer accuracy. So any change in gravity can change the shape of the surface of the segment noticeably, unless it is mounted in a gravity invariant fashion. And therefore, this entire complex optomechanical assembly allows you to make sure that the effect of gravity is not felt on these individual segments. And in addition to all this, India is also making about 100 of these segments also, the mirrors themselves and the polishing of the mirrors to 2 nanometer level surface roughness finish is an extremely challenging requirement, and several of these mirror segments are also being built in India. So as you can see, almost everything under the primary mirror and some of the mirror segments are all being manufactured in India as part of India's contribution to the 30-meter telescope program. So these are just some examples here of these are edge sensor units. They are being mass produced and tested. Many companies, this General Optics Asia Limited in Puducherry and other companies in Hyderabad, etc., are all participating and collaborating with us to fabricate these sensors, test them, and prove that they can sense that level of relative movement between segments at 20 nanometer level. So as an engineer, if you look at this and you want to contribute to edge sensors, if you are good at material science and engineering, yes, that you can contribute to us. If you know how to machine, the various machining process, milling, turning, polishing, coating, etc., all this machining processes, yes, that's involved in building this. You need lasers for doing the laser etching of these patterns. on the blocks, on the sensors, which create these capacitive units. We need to understand lithography, photolithography, or other kinds of lithography techniques. We understand coatings, how to do surface treatments of these glasses and metal. So if you understand and if you're interested in that kind of subjects, yes, edge sensors are pushing the limits, pushing the technological limits of each of these processes, each of these techniques to build these kind of sensors. I also mentioned about actuators, which take feedback from the sensors and correct the positions of the mirrors. These are the complicated actuators which achieve this thing. And you can see that you can have to mass produce these actuators. Many industries in India who are producing these actuators, they are undergoing tests here, make sure they perform, they have all the functionality, they meet all the performance requirements, etc. And as an engineer, if you are interested in, for example, mechanical engineering, modeling, finite element analysis, you need all that for actuators. Again, machining process, these are all mechanical components. There are these voice coil actuators in there. So if you are a electromechanical enthusiast and you understand soft actuators or voice coil actuators or hard actuators, we need people like you. Casting, some of these components have to be cast because they have to be mass produced. That's a technology we need, and some of the requirements of casting in terms of allowable bubble insertions, the surface roughness, etc., and the dimensional tolerance, etc., are all really stringent. So you need to push the limits of casting technology of various ways to build these components. And then finally, as you can see here, testing, not just mechanically testing for functionality, but for electrically testing for performance, life cycle testing, mean time between failure testing, so on and so forth. If you have expertise in any of these areas, building actuators require that. Now coming to segment support assembly, there's those assemblies, optomechanical assemblies, which support at the back of each of those segments. Prototypes were initially built and developed at these companies in Godrej, in Avasarla, etc. And finally, Larsen and Toubro in Coimbatore had been struggling to build these segment support assemblies over the past several years. And we have reached a milestone very recently, as of 1st of this month, when the first segment support assembly has been fully manufactured, meeting the requirements of TMT. And here is a team of Godrej L&T Aerospace in Coimbatore, all happy faces, saying that, look, after 5 years of struggle, we have finally managed to make the first piece that meets all the requirements. It's just a close-up view of the support. So the mirror, this is a system which supports a mirror in a gravity invariant way. May look relatively simple, but some of the requirements are absolutely challenging. Even for a well-established company like Larsen and Toubro Aerospace, took 5 years for them to actually succeed in manufacturing this first piece. So that tells you what kind of challenges exist for engineers in building these components. So for building this, you mechanical engineering, precision machining processes, testing, so on and so forth. All kinds of areas in mechanical and electronics, control system engineering that is required to build and test these facilities. There's another example, some of those sensors, which we call leaf springs. They are the sensors, transducers, which sense any kind of deformations, any kind of stress, which acts on the mirrors and then allow you to compensate for that in the appropriate way. So they need to be tested in various environments. So environment chamber testing, like thermovap testing, electronic testing, etc. These leaf springs have been built by a company called IPA in Bengaluru. And again, here you need to understand thermovap systems, electronic design, fabrication, assembly, testing. If that's your strength, yes, we need people like you for building these facilities. And of course, instrumentation engineers who understand transducers and very, very sensitive transducers, which can sense relative movements at the level of 20 nanometers, and that too over 3,000 such sensors or many thousands of such sensors simultaneously, and then providing feedback to the set of actuators to correct for them. And that is a challenge. So that just gave you a glimpse of, for example, a big program where India is involved in, and how we are rising up to the challenges with participation from industries in India and other large number of institutions and universities and so on. That was about ground-based facilities. And as Dr. Jacob mentioned in his initial introduction, Ayuka is also part of, Ayuka is also building a space observatory, call it Solar Ultraviolet Imaging Telescope, SUIT. It's one of the payloads on board a mission, and a dedicated solar mission called Aditya L1. And there are people at Ayuka who are contributing to this. And then again, like the previous project, this is a collaboration from a large number of institutions in India and abroad. So what is, this is a gist of who is all contributing to the Solar Ultraviolet Imaging Telescope. This is just an artistic view of the satellite. At the top deck of the satellite, there are two instruments. This is called VELC, and this is Solar Ultraviolet Imaging Telescope. And this is just a zoomed up view of the telescope. And these are just a list of institutions and ISRO facilities which are involved in building this payload. So why is it called Aditya L1? That is because the satellite is going to be launched to a point which always lies in this line connecting the sun and the earth. Now there are 5 such points called Lagrangian points. It's called L1, L2, L3, L4, and L5, 5 such points. So this is the Earth, this is the sun, and this is the orbit of the Earth around the sun. So in this system, there are 5 such points. And the first point, L1, lies in between sun and the Earth. And the second point, L2, lies on the other side of the Earth, roughly at the same distance as L1 from Earth, but on the other side. Now, the speciality of these points is that at these Lagrange points, the gravitational pull of the two masses, the sun and Earth in this case, precisely equals the centripetal force for a small object to move around that point. So these points in space can be really very useful to establish a spacecraft around that Lagrangian point so that it consumes very little fuel while remaining in a stable orbit around that point. So for example, the James Webb Space Telescope, which has recently been launched, will be going around in an orbit around L2, which is on the other side of the sun, Earth compared to the sun. And that as the Earth moves around the sun, this point also moves along with it. L2 is always on this line connecting the sun and the Earth. And the James Webb Telescope will be in an orbit around that point. Of course, Aditya L1 is a mission to study the sun. So this point offers as a vantage point. So if you put a satellite here and point all the telescopes toward the sun, that would be an excellent point from which to study the sun continuously, 24/7, 365 days a year, because as the Earth moves around in this orbit, the satellite will always be pointing toward the sun and be continuously being observing the sun. So this mission, this point is about 1.5 million kilometers from Earth. So this satellite will be launched hopefully early next year, maybe January 2023. and it'll take about three months to travel from Earth to this point, about 1.5 million kilometers away, and establish itself into an orbit around this point, so that it can continuously observe the sun. And this payload, as you can see here, is being built, and the building of this payload is being led from IUCAA. And this is just a close-up view of what the payload looks like. It's a SolidWorks model. The light from the sun enters the payload from this side, goes to a primary mirror here, M1, converges, go to a secondary mirror here, M2, and then pass through a shutter, which controls the exposure time, a set of filters, which controls what wavelength of light you are observing the sun at, and then a set of detector assembly on which the image of the sun would be formed. So here is just an illustration of what the sun would look like typically at this wavelength, at the ultraviolet wavelength. This is what the sun would look like. You can see there are many bright and dark areas, and there are many active regions on the sun which are particularly bright. And some of these active regions can suddenly erupt and cause flares, or even eject material away from the sun, escaping from the gravitational field of the sun. And some of that material could actually come towards Earth, and those high-speed charged particles actually can create a lot of havoc in, for example, our satellites in orbit around Earth, and also the atmospheric composition and so on. So our solar ultraviolet imaging telescope would have a field of view of this big, so it will study not just the disk of the sun, but also part of the sun which is around, which is called the coronal part of the sun. These are just some components. This is a primary mirror of the telescope. You can see it's polished to very high accuracy, gold coated. These are some optics. You can see the detector assembly with its multi-layer insulation. This detector has to be cooled to -50 C. So here is an assembly which is being put inside a thermovac chamber to test its operation at -50 degrees centigrade. And this is the full payload being assembled. So you can see the entrance aperture. There's a primary mirror here, secondary mirror here, and the filter wheel, etc., etc. So this is being assembled as we speak at a facility in Bangalore. It's a facility of ISRO in Bangalore, and we plan to hand it over to ISRO later this year so that it is ready for launch early next year. And this is just a mechanical outer box. As you can see, this whole assembly has to be carried out in an extremely clean environment, highly clean environment. So the clean room has to be maintained. So if you are good at vacuum technologies or clean room technologies, etc., here is an opportunity for you to establish these clean labs. This lab was specifically created within ISRO to allow us to put together this payload. It's a highly clean environment. So that was another illustration of a space-based facility which India is involved in currently, where again, as you can see, it's full of engineering challenges at all levels. And then I'm going to give here just a quick movie showing what is called the Square Kilometer Array, which is a radio telescope. So far I had been talking about the 30-meter telescope and solar ultraviolet imaging telescope. They are all both working at wavelengths which are very close to visible light, the kind of light which our eyes can see. But then astronomers also use radio telescope to study celestial objects. And the next generation radio telescope is a very large set of antennae, which will call the Square Kilometer Array, and India is part of that. So here's just a quick movie to tell you what the Square Kilometer Array is. It's called the International Radio Telescope of the 21st Century. So just sit back and watch the movie. We're traveling towards the telescope array. This location is Australia, Australian outback. Part of the telescope is going to be in Australia. So this particular movie is about the Australian part of the observatory. You can see these dishes here. So each of this dish forms one element of the telescope. And you can see many, many dishes around. And as you zoom out, you can see a field, a whole field of dishes spread around an area. And if you move toward the center, there is an area which have dishes of even higher density than the outer area. And in the central part, there is a set of dishes, the set of antennae which are particularly different type. And you can see this entire area. You see the whole big area covered with dishes. And then there are these arms spreading out from the central region in each of these directions. Many arms just spreading out. So it's just going toward the central array, which is made of a different kind of antenna. They are not made of dishes, but different kind of antennae. And you can see this antennae, which is unlike the radio dishes. They look like panels which do not really move, but they can be electronically steered to look at different parts of the sky. And this is just one such unit, a central unit plus a dense area plus a relatively less dense area. And then let's follow one of these arms, which is spreading out. At each of these locations, there is a particular set of dishes. And you can see this, we are now going 40 kilometers away, 70 kilometers away, 100 kilometers away, 150 kilometers away, 1,000 kilometers away, 2,000 kilometers away, 3,000 kilometers away. So this one single telescope, which is 3,000 kilometers in size, made of so many dishes, which all spread out of an area 3,000 kilometers in size, and just forms one telescope. And that is not all. That is just one part of what the telescope is. The full story is that the observatory is so big that half of it is in Australia and the other half of it is in South Africa. Whatever we saw just now was the part which is going to come up in Australia. A similar kind of set of dishes and telescopes arrays will come up in South Africa. It's that big. It's intercontinental telescope. So that is what is going to be. So that is in the radio observatory. That is going to collect light from celestial objects at radio wavelengths. Now let me switch gears again. Just tell you a little bit more about some work which we are doing here at IUCAA in the next few slides, and then I'll stop. I will first mention this project called WALOP, Wide Area Linear Optical Polarimeter. It's again an international collaboration with people and institutions across the world and funded by both government and private funding, like Infosys, Stavros Niarchos Foundation, etc. They are private funders. And there is also National Science Foundation of the US, National Research Foundation of South Africa, etc. are all funding. So it's a multi-collaboration. I won't go into the details. We are building two instruments. One will go to the northern hemisphere, and the other will go to the southern hemisphere, the WALOP North and WALOP South. This is just a optomechanical view of the fully built WALOP North instrument, SolidWorks model. So in order to design this optical system, the optomechanical system, and the full integrated assembly, you need mechanical engineering, electronics engineering. There's a lot of stuff here which are electronically controlled, mechanically positioned. You need to, this whole thing is about 250 kilograms in mass. So when this is installed on the telescope and the telescope moves around to point at different parts of the sky, the top end is attached to the telescope, the bottom end is hanging. Any tiny flexures at the level of 100 micron or of that order would create problems for us. So the flexures have to be controlled to less than a very small fraction of a millimeter, maybe 100 micron or 200 micron at most, and so on and so forth. So the entire finite element analysis and modeling, the full instrument control system. There are detectors, sensors here. Those sensors have to be very precisely controlled electronically, et cetera, et cetera. So it's an engineering challenge. This is another instrument called RoboAO, Robotic Adaptive Optic System, which we can build. You can see this is an actual photo. So you can see this size is about 1 meter by 1 meter. So you can see the complicated optomechanical and electronic assembly, which forms part of such a telescope system. It's just an illustration of how the telescope, such an instrument is mounted on a 60-inch telescope, 60-inch diameter telescope on Mount Palomar in the US. I mentioned that India is planning to fabricate some of the mirror segments for the 30-meter telescope. So I'm slightly changing here again. I'm just trying to give you a collage of the various possibilities. So that 30-meter telescope segments, I said about 100 of those segments are going to be built in India. So what you see behind here is a full fabrication facility we built to make those segments. So this has to be custom built for that purpose. So the entire civil engineering for building this facility is here. So you can see here mirror segments are arriving here from Ohara in Japan. They are being transported and loaded into the clean room facilities, clean room labs inside that facility. And you can see this is inside that facility where we will be building fabricating these mirror segments. You can see that even building such facilities, the civil engineering work, the electrical engineering, the building management systems, all amazing challenges. If you are interested in that kind of activity, yes, we need people like you for projects. We built very complicated electronic systems. These are detector controllers. You can see highly dense boards, about more than several thousand components per side in each of these boards. And we productize them, and other people buy these products from us for their own astronomical applications and so on. So as you can see, these kind of projects which are globally distributed and the construction of these projects are such complex and the requirement for precision are truly path-breaking. In order to achieve these programs, you need a very heterogeneous workforce with various levels of expertise and exposure, and they have to work across the countries around the globe with different work cultures, different industry standards, different languages. What is spoken in Japan is not what is spoken language in the industrial sector in India or in China, and then work across time zones. So you can see that this is not one person, one group, one institute, or even a one country effort. It's truly global programs. And then naturally, these global programs would have to deal with laws and regulations across these continental boundaries, dealing with taxes and duties, labor, environment restrictions, health and safety requirements, intellectual property rights. So if you are a lawyer who can deal with any of these, or you understand taxes and duties, you are a chartered accountant who understands taxes and duties, these programs require you. If you understand labor laws in US, in China, or in Japan, yes, we require your advice on how to manage our labor force for these programs. So, and then on the logistics side, you can see that this large number of actuators, sensors, etc., are being built in India, and they have to be shipped to Hawaii. Some of the components we built have to go to first Japan, where they assemble other parts which they are building on that component, and then they get shipped to some third place or to Hawaii and so on and so on. So the logistic management is an important area. So if you are an engineer who understands logistics, yes, here we need you. And then these projects have very long duration. So human resources management. If you are a good HR person, understand how to manage and retain talent within the organization and keep them motivated over 10 and 20 years of activity, whereas the technology and the landscape itself of how you work is changing over time. Just COVID has completely changed how we work to a large extent. So such changes happen over these periods of time. And in those kind of conditions, how to retain talent, how to keep them motivated, HR, yeah, that's something which we need. Okay, so with that, I hope I gave you a glimpse of what kind of challenges engineers and engineers with additional degrees in management, various kinds of management, logistics, etc., can contribute into these big programs which India is participating. And unless we participate in them and build these facilities, we will not be able to make those fantastic discoveries, which are going to be possible over the next several decades. And it will be great to be part of that story, great to be part of being able to contribute to that fantastic future. And I invite you all, everybody in this group, every young guy who's listening to this webinar, to make an effort to be part of that future. Thank you very much.
Thanks, Professor N. Ramaprakash. Actually, it was a very informative and exciting talk, and I hope it will trigger the students to use their technological advancements, whatever they learn on the future. Now we will move to the question sessions, if there is any. Okay, seems to be. I have a question actually. So my question is related to, I hope I am audible. Yeah, so I have a question. So the surface roughness, actually, it was mentioned like less than 2 nanometer. It is to be maintained for the mirror, I think.
Yes.
What is the significance of it actually? That is one question. And connected to that, so how do we maintain that the same roughness over the period of time? Suppose if we keep the mirror in atmosphere, and so is it like, so we will manufacture the mirror in a way that it will be super hydrophobic, something like self-cleaning, or is it something like periodically we will check it and change?
Yes. So the surface of the mirror, the requirement of the surface roughness comes from requirement of what light gets scattered away. We are looking at extremely faint objects in the universe. So as the light arrives on the telescope mirror, and it has to be specularly reflecting, not scattering. And that puts a requirement on how much the surface roughness can be. And because it's a very large mirror, in order to get to the very high angular resolution it can theoretically offer, the surface roughness has to be equally controlled, well controlled. For a small mirror, relatively small telescope with smaller mirror, you don't demand such high surface roughness. As the telescope becomes larger and larger, in order to reach its theoretical potential of performance, you need the mirror surface to be polished to very fine surface roughness levels. Now, coming to your second question, how do you maintain this surface roughness? Now, once your mirror is polished, you put a coating on top of the surface because the glass itself is not very reflecting. So you put a reflective coating on the mirror surface. Typically, it could be some kind of aluminum coating or some kind of mixed material coating, depending on the particular application. And this coating can degrade over time. So if you remember, I mentioned that for each of the 82 types of segments which are going to be used in TNT, there will be one spare. So the plan is once every 2 years or so, we take out one segment out, put it spare in, and then remove the coating of that segment, clean it up, and put a fresh coating, and keep doing it. So since you have about 500 segments, and if you do it one segment every week, you will take 500 weeks before you complete. So you need to do it very fast. You need to change every segment every day, that is one segment every day. In 2 years, you can complete the 500 segments roughly. So it's an ongoing activity at the observatory. You take one particular segment out, replace it with the spare. That night, observing continues, but that particular piece which is taken out, the coating is removed, cleaned up, and freshly coated. And this, on an average, every segment gets recoated every 2 years, roughly.
Thanks, Professor, for a detailed answer. Are there any other questions?
No questions
Sir?
from the students?
Hello, sir.
Yes,
Hello, sir.
please. Go ahead.
So you mentioned about the mirrors, right? So how much does each of the mirrors weigh, like the weight of each mirrors? And the second part is that does these mirrors have an expiry date, like they after cleaning and replacing them as you told, after repolishing them, does these mirrors need to be
There is no
changed?
repolishing. They will just get recoated. I hope we will not end up repolishing them. That repolishing is a very, very difficult activity. But what is the lifetime? I don't know, 100 years, 120, 150 years. They just, glass doesn't go bad very easily. If you're careful with the handling, if you don't drop and break them or something, you don't hit the mirror on something, typically there's nothing much happens to glass. It will just stay. So the lifetime of the glass is not a problem. The coating itself degrades because of interaction with the atmosphere, and you have to periodically change it. What was the other question?
So how much would the glass weigh after the
Weigh, okay. I will leave it to you as a simple exercise. It's about 1.44 meters corner to corner, 45 millimeter thick piece of hexagon, and your rough density of glass is about 3.5 kilogram per meter cubed, or 3 to 3.5 grams per cc. So you can calculate the volume and find the weight, and you'll be amazed at the number. They're not light. They're not light by any standards. And that is one segment, and you have 500 such segments. Yeah.
Okay, thank you, sir.
Yeah. Thanks, Professor. Is there any other questions?
Is there a chat window or something where people may be typing? I don't know.
Yeah, no, but nobody's typing. Yeah, that's it. Okay, sir. I think it was a very interesting session once again. So we have come to an end of session. I hope all of you have enjoyed the talk. So I would like to thank our principal, Professor P.S. Srijit sir, for inaugurating the Astronomy Club. And moving to the webinar session, introductory webinar session, it's very informative. And on behalf of Rajagiri School of Engineering and Technology, I would like to thank our speaker, Professor A.N. Ramaprakash, for delivering this informative and exciting talk. He graciously accepted our invitation to deliver this inaugural webinar despite his busy schedule, and we remain indebted to him. We thank all the participated students and staff members in this talk. A special mention to Dr. Joe Jacob, Newman College, for his support. The technical support received from Mr. Nitish Kurian and Mr. Akash R. Ashok is highly appreciated. So last but not least, we are very much thankful to the staff members of Department of Basic Sciences and Humanities of RSET for successfully forming this club and to start with the first webinar. So thank you so much. And we will have a next topic coming up, I think in a few weeks of time. We will meet you all. Thank you.
Thank you. I'm again, just to say that I've been very happy to be the inaugural speaker of this club. I wish all the best to the club, and I'll be very happy to provide whatever support I can. Thank you very much.
Thank you.